Welcome back, engineers. We are discussing common techniques and algorithms in system design, and in this video, let's talk about Merkle trees. I hope you're ready. Let's get started. So with this one, we're trying to ask a different type of question. The questions we are trying to ask are, how do you compare two database copies? Right? So we've discussed this during our database replication videos. We talked about how databases must keep copies of each other so that when there is a failover, one of the nodes can take over, right? But this replication is not actually so simple. We cannot transfer entire database copies to each other because databases can be vast. We only want to send a subset of data which have actually been changed or added or updated or removed, right? So how do we do the comparison between two database nodes among a large data set, right? And another example is two file systems. Let's say we are talking about a version control system like Git. So when you look at a code repository, there can be folders, there can be subfolders, there can be folders inside that, and there can be files continuously added, updated, or removed. So how do you keep track of version changes? How do you keep track of entire folder structure and compare it with some previous reference so that we can actually see some dataset changes, right? So again, these files can have large content. There can be text, there can be images, there can be videos, and so on. How do you make sure that only those changes are reflected when you're actually comparing two versions? So those are the type of questions we're asking here. And another thing is, how do you verify a blockchain transaction? So let's say we have a blockchain, there are blocks and each block has several transactions. So you're trying to verify if a transaction is legitimate or if there has been any tampering. So how do you do that? There can be multiple such transactions inside a block. How do you know if a block has been tampered? Right? So in all these type of situations, we can actually make use of a data structure called as Merkle trees. Now let's see how this actually works. So let's take an example of the database nodes. Let's say we have two database nodes, node A and node B. So this is node A and this is node B, and let's say they are in two different physical locations, and let's say they are just keeping copies of each other, right? So they are replicas of each other, and our job is to keep them in sync, right? Let's say we have small data set 10, 20, 30, 40 on both sides. They have been synced and they're all good to go. Now, let's say there has been a small change here. Let's say 10 became 15. So how do we send this data change that 10 has been updated to 15 over a network without actually sending all of these, right? Let's say there has been a new node added. Let's say there has been a node deleted. So all these are changes that we need to be sending from one node to the other node. We definitely don't want to send the entire data set because that is an expensive network operation. We can use something called as Merkle tree. So let's see how that tree would look like for this small data set. So a Merkle tree looks something like this. So let's say we have node A here and we had four data points 10, 20, 30, 40. So what we'll do is for those four data points, we will actually build the leaf nodes. So these are leaf nodes, right? And how do we build these leaf nodes? We use some kind of a hash function. Let's say a SHA-256 hash function or something. So we take the contents of the data point and then we give it to the hash function. We get some hash out of it and we save the hash into a leaf node, right? And we do the same thing for all the leaf nodes like this. So typically all the data points from the database. So the idea is to capture all the leaf nodes, meaning all the data points in the data set, right? So imagine if you have a database with millions of data points, we won't actually need to do the hashing for every particular single data point. We can do some kind of a chunking or partitioning. So we can do grouping of several nodes and then take the hash of this entire group, right? So let's continue. So we have taken hashes of the leaf nodes, and then what we will do is we will combine these two. Let's say we're combining 10 and 20, and we get a different hash for the combination of these two. So let's say we have ABCD, we send ABCD to the SHA hash function again, and then we get some kind of hash like this, ABCD. So we are taking the hashes of hashes and attaching it as a parent node, right? And on the other side also we do the same, and then we finally get to the root node, which is having ABCDEFGH. Let's say this is an example. The hash might be different for different inputs. Just to keep it simple for understanding, let's see that this is our Merkle tree, right? So typically when we are building any tree data structure, we start at the root node and then we start filling the children, right? But in the case of the Merkle tree, we start at the leaf nodes. We build it bottom up. So once we have this, let's say we have also done this at the node B, and we have two different Merkle trees to compare, right? Now let's talk about how we can do the change comparison. Now what do? Let's say our data point has changed from 10 to 15, which means that our leaf node 10 has been updated. So let's say because our leaf node has been updated, its hash will change now. So instead of AB, let's say this hash will be XY, right? And what happens in Merkle trees is if there is a change in any of the leaf nodes, the change is propagated up the ladder up until the root node. So since XY has changed, now we need to take a new hash for these two leaf nodes, and now this is no longer ABCD. Let's say this has now become XYCD, right? And we again need to take the hash of these two children and replicate it to the parent node. So this is no longer ABCDEFGF. This is XYCDEFGH or something similar, right? It won't be so simple hash, it will be a very complex hash, but just to keep it simple, I'm doing this comparison. Now what do? We want to compare two different entire data set nodes, right? So what do? We just compare the root node. If there is any change in the root node's hash, we know that there has been some update, right? If there is no change in the root node, we don't need to do any comparison at all. We don't need to send anything over the network at all, right? That's the beauty of this data structure. So once we know that there has been a change, so what do? We do depth first search in this. So we go to the left child and we see if there has been any change with respect to the compared version. If there is any change, we know that something has changed in this side of the tree. And we go depth of search again until we reach the root node, and this is what we will send. We know that 10 has been updated, we'll see whatever has been changed, and we just send that particular change over the network, right? And if we are looking at the right side, since the child hash is matching with the one on the right side, we don't need to check anything at all in this one. So that makes it a very efficient operation. We are reducing quite a number of checks when we are trying to do depth first search on the Merkle tree, right? That's how Merkle tree helps us compare two large data sets just to see if there's been any change, right? Similarly, when you think about a blockchain transaction, it might look something like this. So let's say we have a block and it has, let's say, 4 transactions, T1, T2, T3, T4. And how do we build it? We build a Merkle tree out of it. We take 4 hashes and we combine these two to make a parent hash. We combine these two, make a parent hash, and we finally get to a root node, right? So if there has been any tampering in any of the transactions, the change would be replicated here, which is propagated to its parent, which is again calculated, and then the parent is ultimately updated. So just by looking at the root node of the block, we can see if there has been any tampering in the blockchain transaction, right? That's how Merkle trees are used. Now let's see how this is implemented in Git as well, right? Typically, Git is a version control system. If there is a folder structure like this, there is a folder A. Folder A has a couple of files, file X, file Y, and then it has two other folders, A, and B. This is the inner folder which has two other files, AX and AY, and then we have folder B which is having another file called PX. So these files can be of any extension. Let's say this is .txt, this is, let's say, .py, and let's say this is .cpp. Maybe this is an MP4 file, I don't know. Maybe this is a JPEG. It can be anything. So what we do is we take the contents of each of these files and then we give it to the hash function and then we get the hash out of it. So let's say we are building a Merkle tree like this. So we'll start at the leaf nodes. We build out all the files. File X content is taken, we get a hash something like this. And then we have a file Y, we get a hash like this. And similarly, we build the entire Merkle tree out of it, right? So let's say we are changing something in file X. This is a txt file. Let's say I've changed just one character from A to B, right? So this changes the entire X from some random hash 268BB4. It becomes something like A to X, Y, T3, something. A large hash is given out, which is simply propagated to the parent as well. Now the parent hash is also completely changed. So this is what we see as a commit hash when we are looking at a Git history log, right? So based on this hash, we can do a comparison with the previous version hash, and we can see that something has been changed, and then we will do depth first search to actually check what file has been changed, and that is what we see as a diff. So that is what we see as a difference in the GitHub repository or in our code changes where we are comparing left to right. So this is how Merkle trees work. So if you think about building this data structure, so we are actually passing in all the leaf nodes to a particular function, let's say a function named build a Merkle tree. And what this does is it hashes each of the leaf nodes, and then it starts building out levels. So it takes a couple of them and builds out a parent, and then takes a hash of the hashes and builds out its parent, and ultimately it gives out a root nodes hash. And that is all we need to do any kind of comparison. So that's all about Merkle trees, guys. If you need any more information or if you have any doubts, definitely let me know in the comment below. Thank you so much for watching. Do like if you found this helpful. Do subscribe if you haven't done already. Thank you so much for watching. I will see you in the next one. Cheers.